Well, I'm back. We're here in chapter 3 now, and this one is a classic. This is where we have our moles and our Avagadros number calculations, the most sacred part of a Gen Chem student's career, or one of them, is right here. This is great stuff. So we're going to go over one of the classic type of problems on calculating number of molecules and moles and from grams and all that stuff. A pretty standard type question, but it has a lot of good stuff in it. So the one we're going to look at is problem 3.90 out of the Brown and LeMay text, and it's closely related to some of the homework problems on the chapter 3 homework list, like there they are, 37, 39, and 41 are closely related to this particular question. And so, as we always do, it's a good idea to take a quick look at the question. So here it is. After doing this stuff for a while, you probably do need a couple of aspirin tablets, so it's a good question to look at here. And it's a pretty standard, straightforward type question here, and it's going to make use of all three of the conversion factors that this particular chapter wants us to take a look at, or that we need to know about here. And so it is molecular weight, G-H-T, boy, that was tough. Molecular weight, which relates grams to moles, grams over moles. Remember, those are the numbers right off the periodic table. Okay, Avogadros number. Avogadros number, which in my mind relates number of anything, 6.02 times 10 to the 23rd, number of anything per mole. Okay, that's its definition. And then finally, the chemical formula of any molecule relates mole of atom to mole of molecules. And that is going to be a critical one in here as well. So this one has a standard, kind of basic introduction and then 3 questions based on it. And the molecule is involved here is aspirin. So let's take a look at it for just a moment. This is what they tell us, that aspirin is a molecule that has the formula C9H8O4. And then they ask us things like, let's see, what do they ask us? They ask us how many moles are in, moles are in half a gram of this stuff, 0.050 gram tablet. Contain, a tablet of aspirin tablet contains a half a gram of C9H8O4. How many moles is that? How many molecules is that? How many carbon atoms is that? That's part A, B, and C. All of that is going to depend upon getting our little fingers on molecular weight. And so we're going to do that one first, and that's a pretty standard, straightforward type calculation. Molecular weight is a basic one. It's the numbers off the periodic table. So for this particular compound here, we have 9 carbons, and each of those carbons weighs 12 grams per mole. We have 8 hydrogens, and each of them weighs 1 gram per mole. And yes, I am using just kind of the rounded off values for these things, which is perfectly sufficient for a problem like this. And we have 4 oxygens, and each of them weighs 16 grams per mole. And if you punch all that out on your calculator, you should come out to 180 grams per mole. That is the molecular weight of aspirin, C9H8O4. And that's the key number that makes all the others work. So, away we go. Part A. Part A says, how many moles are in this half gram of tablet? Okay, we want moles. And you'll notice when I write these, it is a little bit tedious, but I really think it's critical at this stage and later on when you do stoichiometry type problems as well, that it's not just moles, it's moles in this particular problem, C9H8O4. Now, admittedly, this particular problem only has one compound talked about in it, C9H8O4. But in the more complicated type problems, you might sometimes run across, they'll be talking about, number of atoms and molecules of this compound and this compound. And, unless you are really careful, you're going to have grams and moles and all these numbers flying around out there. And you may not know, this is moles. Moles of what? Which one? So I always think it's a good idea, even though it does require a little bit of extra writing, to always label your grams and your moles and your number of molecules with what it is you're talking about. For part A, they want moles of C9H8O4. That's where we're going. And our starting point, of course, is going to be the 0.50 grams of C9H8O4. And here we go. Classic conversion factor type stuff. Grams of C9H8O4 are going to go away. I'm going to turn them into moles. What's the magic conversion factor? Yes, indeed, it's the molecular weight. Grams of C9H8O4. And as we just calculated, that's 180 grams per mole. That's it. That's the only calculation we have to do at this stage of the game. So out comes the magic handy dandy little calculator. I've already done that. And what did I come out with? I came out with 2.78 times 10 to the negative third. Okay? Pretty small number of moles. There's the answer to part A. Part B. Part B says, okay, what's the number of molecules? So when part B is done, we are going to have a number, and it will represent literally the number of molecules of C9H8O4. Number of molecules. You just know when you see that wording anywhere in a problem that your dear, dear, dear friend Avogadros number is going to play a role. What does it connect? Number of things, which is what we're after, to moles, which we've already calculated. How about that? So let's start with that one. 2.78 times 10 to the negative third moles of C9H8O4. Well, moles are going to go away. Number of things are going to show up. And remember, Avogadros number is the number of anything, including C9H8O4. 6.02 times 10 to the 23rd, number of anything in 1 mole. Going to multiply by Avogadros number. That means I'm going to get a fairly large number, and I came out with, when I did it, 1.67 times 10 to the 21st. A lot of molecules. Okay? And there's part B. Part C. And they ask us here, what's the number of carbon atoms? Number carbon atoms in this half-gram tablet. Well, wow, we want carbon atoms. We want a part of the molecule, not the number of molecules itself, but how many of these little dooflodges are in there. And remember, when you need number of atoms in a molecule, that is very often where the chemical formula is going to play a role. And remember, it tells us number of moles of an atom per mole of molecules, which is what we wrote down before, but it also can be used for number of atoms per number molecules, which is how I'm going to make use of it here. I know the number of molecules of C9H8O4, 1.67 times 10 to the 21st. Number of C9H8O4. Number C9H8O4 are going to go away, and number carbon atoms are going to show up. The chemical formula tells me for every one C9H8O4, 9 carbons sit in there. Basically, just take that number and multiply by 9. And when you do that, 1.505 times 10 to the 22nd. A whole lot of those little carbon atoms in one tiny little pill. So there you go. Classic turn grams into moles, moles into number of molecules into number of atoms. A standard straightforward problem. You should be able to work this one quite readily, or any variation of it. For example, if we had told you you have 1.505 times 10 to the 22nd carbon atoms in a sample of aspirin, C9H8O4, how many grams of aspirin do you have? You can work these types of problems in both directions quite easily. They are just classic conversion factor problems like we've been studying for a while now. So take that in mind, study it over a bit, practice a few of the others. Oh look, here's some more to practice. Go forth, calculate. See you later.